Hey everyone, it's Anton, and today we're continuing our exploration of PySpark. Last time you saw how to read in data, how to do some basic operations on it, and perform some exploratory data analysis. And today we're going to dive a bit deeper, looking at feature engineering, doing some advanced aggregates, and finally looking at MLLib library, which is like scikit-learn byte for PySpark. So we'll train a few basic models, compare them, evaluate them, and then save them for later use. Let's not waste any more time and jump straight into the code. Similar to last time, go into my GitHub repository called tutorials and pull the latest version. You'll see inside of the PySpark there's going to be a notebook called Spark Feature Engineering. If you haven't seen my previous video that covers the first notebook, Spark Intro, I highly recommend checking it out because we'll be proceeding right from where we've left. Let's actually see how it looks like. You can see that when inside of this feature engineering notebook, we are reading in a Parquet file called process.pq, and you can see that we get it at the very end of the Spark intro notebook. So that's why I recommend you first of all go there, run the script, or if you haven't seen the video, I highly recommend checking it out first and then going back into this video. Similar to last time, we're importing a few things from PySpark library. First of all, we import Spark session. This is used to initiate our Spark session. Then we are importing window, which is going to help us create our window functions. Then all the functions that are going to be used in aggregations and to select specific columns are coming from the functions. And then we're importing a lot of things from the ML library, and these are going to be a few of the preprocessors, the pipeline, and then the model that we will be building, which is random forest classifier. All of this is contained inside of the PySpark, so if you've already followed the steps to install PySpark in the previous video, then then you don't need to do anything new. And let's import them. And also let's initiate the session. Connection refused. This can happen sometimes when your session was idle for a long time, so you'll need to restart the kernel and follow the steps again, and all of it should be working then. You'll also notice that it's using this address to initialize it, and what you can actually do, you can copy it and then go to the your web browser and then just add 4040. That's usually the port where your PySpark jobs are, and you'll see the UI for Spark. You will see some of the events that have been running. So recently I haven't been running any jobs, that's why I don't see anything here, but let's see if it fills up as we go through the notebook. First things first, let's read in the data. And here I'm actually already doing something with the label column. In particular, I'm encoding it that if it is equal to benign, then it will be 0, and if it's equal to malicious, it's going to be 1. Or in this case, I'm saying if it's not equal to benign, then it should be 1. So let's run it, and it's going to take some time to read, and I'm asking to show 5 rows, so that's exactly what it's going to show me. And you can see this is the data that we saw last time as well, except with the new column called is bad. So this is something useful again that you can use. That's as you're reading the data, you can already apply some transformations to it by chaining this with column method. We have our data, so let's jump into the feature engineering. As you know, this dataset contains logs for the IoT device activity, which sends specific packets from one source IP to a destination IP. And there is a time component to this data. So whenever you have a time component, it's actually a good idea to create some time-related features. So for example, in here, we can engineer features like number of times we've seen this source IP in the last minute, or the number of times we've seen the destination IP in the last minute, and the same can happen for the port. We can create the similar aggregates. So count, we can also do, for example, averages, or we can do maybe on another with time window. So maybe not instead of the last minute, how about we take last 30 minutes or maybe last 10 seconds. So all of this is possible using the aggregation functions. Specifically, we'll be using window functions that you will see later on. Here, I define a set of functions to help me engineer these features in a very systematic way. For now, let's just define them. And you will see that in this cell, you will see all the features that I'm trying to engineer, and I'm engineering them all using one function, just changing the parameters that I put in there. So let's see what this function actually does and how you can create these features yourself. First things first, how does the window function work in PySpark? Let's say that I wanted to calculate a feature called source IP count last minute. And we can do it first of all with column, because we want to create a new column, and then we specify the name, and then the aggregation that we want to do is simple count. Usually you need to specify what column do you want to count. Here it doesn't really matter because we'll be counting the number of rows. Here it can be anything basically. But then we also need to specify the over clause. If you're familiar with SQL, that's how the queries work as well. You need to specify the over, and then you also need to specify the partitioning. To specify the partitioning in PySpark, it goes through the window function. So you specify a window, and then you need to specify by what do you want to partition this window. So I want to partition this window by source IP, because I want to count how many times has this particular IP appeared, not just all the rows, how many times have any IP appeared, right? And we can run this. This is going to be all right. And now it's going to think. And once it's done thinking, we have this feature, source IP counts last minute, but it's not 100% correct. How can we check if this is exactly what we wanted to calculate? We want to select a specific example of IP. So let's format it a bit, and let's do a filter of the IP that will be equal to this particular IP that I selected prior to this video. And we also want to order by the DT, right? Because we want to, our feature should be rolling. So it should be counting how many times has it appeared prior to this appearance, right? So let's check it out. And we can see that this feature is going to be constant over all these instances. And it's going to be like this because we haven't specified the period in which the window should be. So currently the window is unbounded. An unbounded window means that it's essentially just counting how many times has this source IP has appeared. And if we check count, simple count, it's going to give us 20. So this is what we see as a value for this feature. It appears 20 times. How can we bound this window function? Well, we can do this by first of all ordering this partition and then arranging it between specific time frames. And I have created a handy function here. So let me just copy paste it because I also don't remember all the syntax. Let's add this step here. And let's substitute the timestamp column with DT. And then I'm also telling it to arrange it between. I also have this handy function of minutes to seconds. And whenever I say just 1 minute, it's going to translate it to seconds. So it's going to be 60 seconds. In this case, I can just specify minus 60 because I know how many seconds are in 1 minute. Here you can see that I'm also casting this date column to long. And this is done to be able to use this range between. So range between works only for the numeric values. It doesn't work for the dates. So we wouldn't be able to specify the range between 1 day and 3 days. But instead what we're doing, we're casting it to long, which is number of seconds. And then I'm telling it how to range it. So this is going to be from the previous 60 seconds to the previous 1 second, which ensures that we don't leak any data. And it creates this 60-second window. And now let's rerun this query again. And we can see that now it's all 0. So what happened? Well, it's because there was no activity in the previous minutes for any of these rows. So for example, here, this is the first row. So this is expected to be 0. But now we can see that this activity happened at the minute 25 and this activity has happened in the minute 21. So there is roughly 4-minute gap. And this, we can see here that it's going to be the same for all of the rows. Hence, let's extend this maybe to, and here's our little function going to come in handy, minutes to seconds. Let's say minus, and then I wanted to say 5 minutes, you know, the previous 5 minutes, how many times? Let's run it again, and we finally see some numbers. Here, yes, it has appeared there was 1 additional activity in the previous 5 minutes. Here we see even 2, so there was 2 activities in the previous 5 minutes, right? So at the 36-minute window and at the 33 minutes, and the activity has happened in the 37, so the 5 window matches, and we can just sense check that all of them kind of happen in the specified time window. So that's great, and this is how all of these aggregations are going to work. The only thing I did with these functions is to parameterize it so that when I'm calling generate rolling aggregates, right here, it's going to create, first of all, the same thing like f count. I also added an option to, for example, make a sum or make an average. And the only thing that changes here is this function that I'm calling here, right? So it's going to be average or it's going to be sum. All of this over clause remains the same, and the over clause is where I generate a window. So generating a window is one thing that you can parameterize really well. And here I can specify by which column do I want to partition, which column should be turned into a timestamp, and then what type of range do I want to have. And here I'm using the minutes to seconds function that you saw previously. So that's basically how it works. You could also generate these features in SQL, for example, because their analytical functions are supported much more, and you can actually create some sort of analytical functions over the time range windows. But today we're focusing on Python, so that's how we'll do it. Now, when you run it like this, you can see that it's instantaneous, right? It's 0 seconds. And why does it happen? It happens because, again, the execution is lazy. It's something I told you in the previous video. So when I called it like this, it didn't actually do any sort of calculations. It just defined what calculations it's going to run when I call something to view the data. It can be show, it can be collect, or it can be any other operation that forces it to produce some sort of an output. And if I do df.show, let's show the first 5, only then is going to make these calculations, and you can see it's thinking quite a lot. That's where we can actually go here and look at the jobs that are being submitted. And here we can see that this is the job that's taking place now at 14:24. And we can see that it's still running. It's shuffled 12.6 megabytes. And yeah, it's just running. You can see that it hasn't failed yet. So that's all good news. You can also kill it if you want. We can see some additional details about what's happening. And we can see here that it has completed running. Took us roughly 1 minute, and we can see the output here. Now, obviously here it's null because there was no previous activity, but they're going to be not null whenever you have some activity prior to this transaction. Now, obviously this is not perfect when we just want to look at data and maybe we want to, I don't know, print out a row of columns or something like this, and then it would create this calculation all over again. That's why I recommend, after you've done some sort of this heavy aggregations or like heavy processing, if you're doing the exploratory analysis in the interactive way like I'm doing, just write it out to the Parquet file. Here I'm going to write it out to the feature engineered, and I already have this feature engineered Parquet. So that's why I'm specifying a mode overwrite, but you probably won't have it, so you can actually delete it. And it will take some time to write it out, but once it's finished writing, operating on this data frame is going to be much easier, because then we'll just be able to showcase the data frame without needing to recalculate everything. And this is one of the advantages and disadvantages of PySpark, is that lazy evaluation is in theory very nice when it's running kind of as a standalone pipeline and you want it to be super optimized. But whenever you're working in the interactive mode and you want some of your results to be cached and stored, this is not perfect. So that's why sometimes you just need to write it to disk and then read it from disk, and then it's going to be much faster. And as you can see, writing it out takes a long time as well. And it is exactly because it needs to recalculate all of these features again. So you can see that like 1 minute and 6 seconds was probably taken by the calculation, and then writing this data took additional 15 seconds. But now what we can do, we can read it in, and it's going to be very fast. And now when we want to show it again, it is almost instantaneous because it doesn't need to do any calculations, and we're seeing still the same nulls here. Yeah, these two data frames are going to be the same, df and df-fe. You can actually delete the df if you want. You know, we can do delete df. So we have engineered our features. Now let's try to build a machine learning model and see what type of performance we can get to classify malicious IP activity versus benign IP activity. Let's first of all denote the features that are numerical and categorical, because they will need to have separate processing. You can see the full list of features by calling df.columns, just like in pandas. And here, because this list is going to be quite long, I'm going to limit it to 5. Oh, df we already deleted, that's true. So yeah, you can copy paste them here and continue with the next steps. And the next step is going to be a bit of a pre-processing still, because we have some categorical features that have too many unique values. And these unique values are also going to be quite rare. In this case, it might be best to get rid of them if we want to optimize our machine learning performance. How to do this? First of all, let's count the number of unique categories per feature, and we can do this. Let's first of all define the categorical features. Here you can see that I'm doing this in the list comprehension form. So I'm doing a function count distinct column, and then operating over the categorical features, and then just doing the show. And this shows me that before we remove anything, there is actually 167 unique categories inside of the history. So that definitely might be too many, especially if they're quite rare. And how do we define the rare categories? I'm finding the infrequent categories by first of all finding what are the frequent ones. And here I'm doing this by iterating over the categorical features and then doing some logic here. You can copy paste it to see what exactly it's doing. I can maybe show it to you on example of one feature. This is again like a very nice example of how handy the chaining is. Here, let's select actually maybe the category history. And what we're doing, we're first of all counting, grouping by the history and counting. This is similar to value counts in pandas. And then I'm filtering only those that have more than 100 appearances, because in my opinion, this should be enough for the model to learn the required patterns. And then I'm going to select the columns that are left, and I'm going to translate them to a list, or more specifically to pandas series, and then kind of unraveling it to one-dimensional attribute. And we can see that the result looks like this. These are the values that appeared frequently enough, and we want to include only them into our data frame. Now let's delete this and let's see what happens after this. So here I'm using a kind of if-else scenario, except I'm using when and then otherwise. That's another kind of nice utility by PySpark. Here I'm saying that, okay, if like when this column that I'm operating on, the categorical column, is in the list of the categorical valid values that I generated previously here, then I want it to be the same value as it is. So don't do anything with it. Otherwise, fill it in with the value of other and then rename it to keep the same name, because otherwise it would have very long name of the chained operations that we did. So once we run this for all of the categories, we can see, okay, how many unique values are inside of each category after we filter out the infrequent ones. And then we can see that the numbers have dropped significantly. So this is going to be, first of all, easier for our model to learn. And then also it probably also going to overfit much less, because there's going to be less infrequent categories. Now that this pre-processing is done, let's go into the required part of training and test split. In this case, I'm not doing just a random split, although it is possible to do in PySpark. We can just Google, PySpark train test split, and then it's going to lead you to the train validation split for tuning, or there's also going to be a few other methods. So just kind of, pick your own poison essentially. And there is a random split method. So this is how you can do this if you would just want a random split. But I don't want just a random split, because there is some leakage that can occur if we include the source, the activity of a source IP into both training and testing. That's why we're going to split according to the IP address. So to do this, first of all, let's show the number of times that a source IP is registered as bad, so as malicious. And we can see that in this data set, there is only 2 IPs that are malicious. This one, I guess, is just a subset of this one, so we can ignore it. This IP address occurs about 500,000 times, and this IP address occurs 150,000 times. So in my data set, I probably want to include this into my training set and this into my testing set, kind of just to simulate a scenario that, okay, we saw this activity in our training, So we know some parameters of a malicious activity, but then this IP address appears. So what do we do with it? How would the model classify it? And this is the test set that we want. But then also we have a large body of not malicious ones, right? So how do we do this? Well, again, PySpark is quite flexible in this regard. In this cell, I'm specifying, first of all, that I want to filter out those malicious IP addresses, and I end up only with the list of not malicious activity. And then I select the source IP and also create a new column called isTrain, which is a constant of 1. After this, I drop duplicates. So I'm essentially selecting distinct IP addresses, and then I'm randomly selecting 80% of those IP addresses. And this is going to give me my train IP's data frame. And we can run it just to see what is inside of it, right? So we can show maybe first 5 rows. This is going to be it. So you're just going to have a source IP and a flag isTrain with the training IP addresses. And what we do then, we just join it to the main data frame. And in this way, our data frame now is going to have the flag, is this IP address a training or is it a null, which is going to be a test? So here you can see that it's isTrain and it is null. So the first 5 rows in our data set are testing. The final step is for the selection of the training and testing data. For the train, I want to select where the flag is train. And then I also want to select this first IP address that you saw here. So it's going to be this or condition, right? I want to select if it's isTrain or if the source IP is equal to this one. And then for the testing set, I'm going to select if the isTrain is not equal to 1, or I could also specify that it's null. And then I want to specify, okay, and that the IP address is equal to this. After doing all of this selection, this is going to be my training and this is going to be my testing sets. We can check what's the proportion. It's not going to be perfectly like 80-20 split, mostly because the counts of the malicious activity is way too high for this one when we compare it to this one. But we can still see what type of count do we get. And we can also calculate what's the proportion, what's the percentage of the testing set. Usually we would want it to be 20%. Let's see how did the random split do it. It's 13%, which is not perfect, but I think it's enough for the training and testing split since the counts are so large. So I hope this was clear and the motivation behind this type of splitting is also clear. Always be aware of your data properties and in what way you could potentially leak data, because if you design your training and testing splits in a bad way, this means that your model in production will be underperforming and you won't be sure why. And most of the time it's because of the bad training and testing split. Finally, we have our training, we have our testing sets. Let's begin with building the pipeline for machine learning. Machine learning in PySpark is very different from scikit-learn. There is fits and predicts and transform methods, but they work completely differently. I'll show you a few examples later. In here, you will see that I have 3 steps in my pipeline. I need to do a string indexer. This is essentially label encoder. So I'm telling it which categorical features there are, and I'm telling it to encode them into numbers. And you also need to specify what are the input columns. There's going to be my categorical features. And you also need to specify the output columns so they cannot be the same. You cannot transform them to the categorical features. You need to create a new set of names. Here I'm calling them categorical features indexed. And if you remember, here I actually did it just by appending index to the categorical features name, right? So that's how it's going to look like. And I'm also specifying that if there is a new value that comes into this pipeline, that I want to skip it, so not do anything with it, but instead put it into a separate bin of unknown values, which is how scikit-learn does it as well. Second part is the vector assembler. So this is how PySpark does its machine learning. It operates on the vectors, and you will see how it looks like later on. But basically, again, you need to specify all of your input columns, and you need to specify into which column it's going to be outputted. So you can see here that it just outputs it to a single column called features. This is a default name for it, and features is going to be an array of all of your input features essentially. Finally, the model is going to be random forest classifier, and here I'm specifying what's the label column. The label column is going to be isBad, and here I'm also specifying some of the parameters, like for example, number of trees is going to be 100. We can also specify maximum depth, maximum bins, but for now let's just keep it as default as we can. Pipeline works in the same way. You just specify stages and specify a list of these stages, and we can run it like this. Again, nothing happens because nothing is fit. Then what we can do, we can fit the whole thing on the df train and then transform here in a way that it makes a prediction and gives you back your original data frame with appended columns for probabilities and for predictions. But before we do that, let's actually do it a bit separately to see what each of these indexers and assemblers does. And for this, we can do index fit, we can do df train, right? And you need to reassign it back. Don't forget, this is a big thing here. You need to reassign it back, so you can see pipeline.fit, I'm reassigning it back to pipeline, and for the indexer, I'm reassigning it back to the indexer as well, because they cannot be modified in place. You always need to be explicit when you want to overwrite a variable. Let's fit it. It is fit, and when we call index transform, let's transform the train features as well, and we can show the first 5. We can see that it has created additional columns called service index, proto index, connected state index, history index, just as we've specified in here in the output columns. So this is the first step it does. So let's save it into a temporary file. Don't want to use it later on, but for now let's just save it. And then for the VA, you don't need to fit it, but you need to transform it. So what do you want to transform? We want to transform the temporary, right? And this is going to give us a data frame, and we can show it, and it's going to add this features column here. And as you can see, the features column is going to be an array. An array is going to be quite weirdly looking. It's going to contain all of your features, but then some of them are going to be encoded in a bit of a different way to save space. Let's actually, maybe select a random sample of 1, and then let's select the features column, and then I want to show, and I don't want to truncate. And these features are going to look like this. So it's quite hard to read, but your PySpark model will understand it. And it saves space as well, so that's great. So let's delete all of this. Now you know what it's doing, and your random forest classifier is going to be trained on these features. You can actually see that you specify here features column. So let's make it explicit that it needs to use features, but it does it by default, right? So let's fit and let's transform the df test.
A little longer than a few minutes later.
Perfect. It has finished training in 40 seconds. And what we can do now, we can evaluate the model. MLLib has its own evaluator classes. So it has a binary classification evaluator where you can specify what's the label and also what's the metric that you want to use. And for the binary classification, it has 2 values. It has area under ROC. So again, let's make it explicit, but it's set by default already. And we can, just copy paste it here. And we can evaluate for both. Let's see. And the results that we get are not that good in terms of the raw QAC. It's just 55, but the PRUC is very high, which is usually strange. It's usually the other way around, but I guess in this case, PRUC just doesn't matter because it's not, the data set is not that imbalanced. And instead we are more struggling with raw QAC. So that's quite interesting. Let's see what's happening. Why is this a case? You can usually diagnose some problems with your model by checking the feature importances. That's exactly what we are going to do here. Random forest classifier has inbuilt feature importances, and we can get it by accessing the pipeline stages. You can see this thing that I have here. So we're accessing the pipeline, we're accessing the stages. So -1 is going to be the random forest classification model. That's how you can access it. You can also access, for example, first string indexer model, or you can access the vector assembler, or you can access the random forest classification model. And then we can get the feature importances, and then also we can get the input columns from the previous stage, the vector assembler, and construct our data frame. Here I'm using pandas just to make it a bit easier. And we can see that the most important features are destination port count last 30 minutes and the destination port count last minute. This is interesting. So let's do a quick analysis by grouping the data frame by the hour label and then checking what's going to be the average of these values. This is going to give us a rough indication of is it actually useful. And we can see, let's actually go to the df train and let's do that show. And we can see that indeed there is a huge difference in this value, right? So the port count in the last 30 minutes is huge when it's malicious, and it's very small when it is not malicious. And then let's see if this pattern generalizes to the test data. So we can see here that it's actually not generalizing that much. We can see that in the test data, the port count is actually quite large already in the non-malicious. And then for the malicious, it is a bit larger, but not by that much. So this feature is very useful in our training dataset, but it's not useful at all in our testing dataset. And this is sad, but this is how it is. So this is a good indication that we might want to exclude these features from our model and spend so much time engineering them, and they turned out to be not the most important ones, or not the best ones, but that's okay. And then I guess I'm also going to exclude the IP counts, destination IP counts as well. Maybe there's also some sort of an issue with them. So let's create this again. Let's run this. And I don't need to run the kind of pre-processing of the categorical features. All I need to do now is to rerun the pipeline. So to redefine the pipeline, because I've redefined my features. And I want to run the fit predict again. Going to take some time again. So I'll see when it's finished training.
Much later.
And the training is finished. It took roughly the same time. Now we can redo the evaluation. And we can see that the ROC VDC is much better now. It's 0.97, so this feature was messing everything up for us. That's perfect. Good way to diagnose features, keep that in mind. And we can see that actually proto index and history index, so the categorical features, become the most important ones here. Brilliant. So we engineered a lot of features. We trained our model using basic random forest classifier. We evaluated it, found out that there was some sort of an issue with one of the features that we've done, diagnosed it using feature importances, and then retrained the model again, achieving much better results. For now, let's call it a day. Great job. It was a good introduction into MLLib and to more advanced feature engineering in PySpark. What we could do now, we can save this model for our later usage. To save it, what we can do, we need to, again, access the stages 1 classifier and then just do save. And we can save it in the RF basic, right? And it's going to save it into the folder like this, where we see some data, some metadata, and some trees metadata. However, what's going to be much better is to save the pipeline itself, because our pre-processing steps are going to be remembered. So it's going to be quite nice to be able to deploy just the pipeline and not a model, and not a single model. And oh no, we got some errors here. We can see that RF basic already exists. Well, yes, of course. So we can call it pipeline basic. Saving it up, and we can see that it's saved here. And inside of the stages, the elements were saved separately. Similar thing here for the random forest classifier, but then we also have our vector assembler and we also have our string indexer, and all of them are going to be available to us for later reuse. That's it for today's video. I hope you found it useful. Don't forget to like and subscribe and comment. I greatly appreciate it. There's going to be more PySpark videos coming up soon. We're going to be looking at how to tune our hyperparameters and how to deploy these models and maybe even deploy data pipelines. And then afterwards, I'm also planning to look at the streaming capabilities, so stay tuned. I'll see you in the next one.